In this tutorial, I'm going to talk a little bit about using GIS workflows and creating them in Grasshopper and Rhino. For those of you who don't know, GIS stands for Geographic Information Systems. I'm actually not going to introduce GIS as much because this tutorial assumes you have a working knowledge of what GIS is. But suffice it to say that any kind of mapping that uses data to create heat maps or process it to create any kind of conclusion in regards to space and information and representation is probably using some sort of GIS workflow or methodology. And oftentimes GIS is done in platforms such as ArcMap or QGIS, which is open source. But in this tutorial, we're going to talk about how to use that or to do some basic GIS stuff in Rhino and Grasshopper. Now, just before I get started, I'm going to explain the workflow a little bit. What we're going to do is we're going to take the shapefile, which is the file that contains geospatial data, and we're going to load it into Grasshopper as geometry. And then we're going to bake that geometry so that afterwards what we have is we have Rhino geometry in a Rhino file with the data embedded in the Rhino file, embedded in the metadata of the geometry. And then using that Rhino geometry, we can then load it into Grasshopper and reference it from Grasshopper and select selectively certain parts of geometry from Grasshopper. And then from that, we can get the data. And the reason why I think this workflow is really interesting is because you can do a lot of kind of three-dimensional computational calculations with 3D geometry, with geometry in Grasshopper that you wouldn't otherwise be able to easily do in QGIS or ArcMap. So quickly, the first thing you need to do is install Grasshopper Python, GH Python. And if you haven't done that, you should do that by going to the Food for Rhino website. On the skill tree, skilltree.gsap.org, there's a tutorial on how to use plugins. So if you're new to the plugins and using Food for Rhino, look at that. It's a pretty short tutorial. Essentially, you need to download, log in, create an account, and download the most recent version of the Grasshopper Python plugin that lets you use Python in Grasshopper. It's kind of an amazing kind of tie-in between the larger world of Python and imperative and programming with Grasshopper's kind of scripting language. After you do that, then you have to look for a Finch's component, and if you Google for Finch's Grasshopper, you'll find it. As of October 2013, there's a forum or a page on the Grasshopper 3D website. And you can download the file. Actually, the best file to download as of right now is in one of the the discussion forum posts called Finch's Import SHP File Component. If you actually keep on scrolling down, there's someone's component called Finch's Fix by Carlos on September 17th. Download this. And you know, a lot of things on the internet are actually the best information on the internet are in forum posts and not always in you know, a blog post or kind of published form. So this is kind of the universe you'll get used to when you do more and more interesting stuff in computation. A lot of the information is, you know, people asking each other and people answering. So that's the component we need, and actually if you open it in Grasshopper, you can see that there's two main components here. I'm actually going to turn this off. So this one, first of all, these are Python components, which is why we had to install Grasshopper Python. So I'm going to bring that in here. What this does is it loads the shapefile as Grasshopper geometry. And what this one does is it reads the data from the geometry in Grasshopper, the shapefile extract user strings. And this is because each geometry in Rhino actually has this thing called a user string where you can insert any kind of information. In this case, the kind of the data from the shapefile is read and stored in that metadata in the user string. So this is why it's called shapefile extract user strings as a component, and this is why it's called read shapefile. So then we need a shapefile, and what I'm going to do is we're going to go get some map Pluto data. And Pluto data is a bunch of data, a huge data set about each tax slot. That's, I think, merged from the Department of Finance in New York City and the Department of City Planning. So if you go to download, and this site is on a site called Bytes of the Big Apple, and if you Google Bytes for the Big Apple map Pluto, you'll find this page. and each borough is listed as a shapefile. We're going to download Manhattan. As an interesting note, you can kind of see kind of different sizes, just roughly. Queens' shapefile is 6 times larger than Manhattan's shapefile. So we're going to download that shapefile, and that shapefile has a lot of interesting data in it. I won't go too deep into what kind of data it is right now, but I'm going to extract it. mn.pluto, you can see there's a folder in Manhattan, and you see all these files. And what we're interested in, or what we're going to use most oftentimes, is the shapefile. And the shapefile is spatial geometry, polylines, points, etc., that have data associated with them. So you could get, a shapefile of all the rivers in the U.S., and you might have a bunch of polylines that each polyline represents a river. But the shapefile usually is, pretty large in size, and a lot of this other data is used by, storage for like data storage or metadata about the data set. And oftentimes you'll also see a file in the directory. This is just good practices. Well, it'll explain all the different fields of data that you have in your data set. So we have zoning codes, we have the building class, the land use category, the built FAR, etc., etc., etc. So now we have a data set, we have this tool, or this component, Python component called Finches, and we're going to load this. Now what I'm going to do is I'm going to create the file path component, and the nice thing about this is when you right click and set one file path, you can actually then go into a directory, the one we just opened, and find the shapefile and click on it, and it'll actually turn it into a string. So you can see now it's given us the location of the file path. Now with this component, what I'm going to do is I'm going to unclick read to center, unconnect it, and the reason why I'm doing that is because when Grasshopper loads this geometry, it tries to be helpful, or this component tries to be helpful and moves everything to the center, the XY center, 0, 0, of the Rhino space. But this isn't always helpful, because, for example, if you had a rivers shapefile and you had a mountains shapefile, it would not always move them to the exact center and they'd be misaligned. So as a general principle, I try to keep move to center turned off. And now we're going to double click on false and start reading the file into Rhino geometry, and it started working, and I can tell because it's really slow. I can't pan around. It says it's not responding. Oftentimes this will take, like, say 25 seconds, depending on the speed of your computer. And once it loads, all of a sudden, the window will stop being gray. I'm actually going to skip. Oh, there we go. So now we're here, and the file is loaded, and it looks blank, but we can see that there are 42,000 pieces of geometry, and if we zoom out far enough, you can find this other piece and zoom back in. If you're having trouble doing that, that's actually okay, because what we're going to do right now, is take these 42,000 pieces of geometry, and I'm going to right click and bake. And I'm going to bake them into a layer called Pluto Manhattan for now. And you can tell I've baked everything because I can then select them in Rhino and not Grasshopper. And I'm going to double click on the true and turn this off. So this is done. I'm done with this step. And the nice part about that, I'm going to select everything and zoom extends. So the nice part about that is now I have a Rhino file that has all this data in it as geometry, but this is not just a line. This has a lot of rich data, metadata including into it. Just to prove what I'm talking about, I can select a bunch of curves. So now here we have the Rhino geometry. And you can see I have all these polyline curves inside of here. But not only are these just curves, I can now plug this into this component that it will extract the data from my geometry. And you can see all the attributes inside of each data. And each point of data has all these different attributes and all the different corresponding values. And this shapefile, the map Pluto shapefile, happens to have, let's see, I don't know, 40, 50, 70, 80, a lot of different fields or columns. And I can do this, so one thing I can do is say, okay, I want the year built, so that's the 9th item. So I'll create a slider, create the item, so this will get, from a list, I'll get the 9th item, and I'll get all the year built values. And now obviously these are not the values, these are just the names of the attributes. But instead, if I also plug this from get the values and get the 9th item, so I get all the year built attributes, and those correspond to these values. So the first piece of geometry is built in 0, 1929, 0, 0. And here's another lesson with data: it's not always accurate. So 0 might mean a lot of things. It might mean that there's no record data. It might mean that it's invalid. That you would have to go back to the PDF and kind of look at the data methodology and say, why is this 0? What does that mean? And depending on what that means, it could be like it could be anything from they don't have a record to it's inaccurate, or anything. So one thing I could do, for example, is I can instead of I could let's see, I could make a gradient between, right-click presets, say 1900 and 2000, and so the older buildings are black and the newer buildings are white. If I plug this parameter into it, then I get all these different colors that correspond to my scale. What I can also do actually is, like here, I can flatten all the data, and the reason why I'm doing that is because when I'm going to do a custom preview with this geometry, I want to have the geometry going in to the custom preview be a list, and the colors also be a list. So now that worked. I can also do boundary surfaces, which, given a bunch of edges, creates a bunch of surfaces. So instead of lines, I'm actually then coloring these lots. So now I have this kind of heat map, or not heat map, chloropleth map. So the lighter ones are new, the darker ones are older. That's actually a pretty wide spread of values. So this is kind of fun. But again, part of the reason why we want to put this into Grasshopper is because there's a lot of fun things you can do with kind of spatial calculations. So I'm going to do another test in which I have, say, this geometry. I'm going to select a little piece of geometry as a test, and this is always a good thing to do, is to always work with small amounts of geometry at a time. And I'm going to draw a curve that kind of passes through this to simulate me walking through this area as if I could walk through walls. So now I have my geometry of the lot areas, and I have this curve representing a path I took. And I can go into intersection and then click on curve, and I'll grab all the intersections between curves, the lots, and this curve. And you'll see I get a bunch of points. So what this means is, on this first lot didn't intersect with anything, so that there are no points. This lot intersected with 2 points with the curve at 2 locations, which makes sense. The curve enters a lot and exits a lot. And what I want to do with this is I want to actually use this data to filter out the lots that intersected with the curve or didn't intersect with the curve. So I'm going to, there's many different ways you can do this, but here's one way. If you think about it, the number of points a lot intersects dictates whether or not it intersected with my walk curve or not, right? If I didn't intersect with if there are no points of intersection, or if the number of points were 0, then I didn't intersect with my curve. So I can say, okay, what are the number of points in this list? And the output of that is a series of numbers, 0, 0, 0, 0, 0, 2, 0, 0, 0, 0, etc. And then what I can do is I can use the Boolean component to force or to cast this into true-false values, and anything that's 0 will become true, false. Anything that's non-zero will become true. So now 0 becomes false, etc. 2 becomes true. Now, if you think about this again, what this is doing is the number of points correlate to whether or not, if there are no points, it means that it didn't pass through, so it's false. If there are any points, it means that it did pass through, my line did pass through the lot, and it's true. So then I can use the dispatch component to sort pieces of geometry that did collide or did not collide with my kind of walk path. But this is pretty important. I can't just plug this in because I'm plugging in a list and I'm plugging in a tree. And what that would do is it would compare the entire list with the first item in on the tree, the entire list with the second item on the tree, etc. What I need to do is flatten it. And this way I have kind of a flat list of 215 values. My geometry has 215 values, and that way when we compare them, it'll compare the first item in the list with the first item in the list, second item with the second item, and so on. So now, with the dispatch component, you can see it's selected only the curves I passed through, which is fun. And now, that means I can take this geometry, plug it into my earlier process. So only the curves I passed through will be colored. And instead of doing that only on this little patch, I can select all the geometry and have my kind of a geometry collision check for every lot in Manhattan. And of course, I don't have to be content with a flat surface. I can take this geometry, each individual piece, and extrude it in the Z direction. Let's say, make it a chunk. I'll cap that geometry also. Instead of a surface, I can work with geometry. And then I can have, for example, I can draw a line that say goes from Columbia, walks down, goes through Central Park for some reason, Midtown East, loops around Union Square, goes to the financial district, and somewhere out into Brooklyn. And if that line is my hypothetical walk or fly through the city, and I use that as my collision line to see which lot lines was I walking through, and I'll actually also kind of hide all the geometry just to make it clearer. And while I'm at it, I might as well change the color of this layer to be kind of a lighter gray. Then you can see that I've effectively calculated this walk through the city and got only the buildings that I intersected with. And now it's extruding them in equal height, but coloring them according to the year they were built. So the lighter ones are newer and the darker ones are not newer. So you could do something interesting and say, like, aggregate all the information and say, based off of your walk in the city, you were walking through a neighborhood with mostly older buildings, except for Midtown East, where the sun is turned gray. And you can gather that data and represent it. And of course, all the spatial operations, you could extrude all the buildings not based off of a random height, but based off of a year they were built. So if we did that, all our buildings would rise in this funny way. And since the buildings are they're built in 1900 to 2000, the difference is a little bit harder to spot because they're all kind of extruded by at least 1900 units. But you can do any kind of spatial operation here, and so hopefully this starts to get you a little bit of an understanding of what's possible. The sky's the limit. Right now, I've just got created an intersection between this kind of wandering path and all the lot lines. But you can do things like using ISOVIST, and this is has to do with kind of vision. There's another tutorial on the GSAPP skill tree that will explain ISOVIST. But you can do things like get me all the buildings that I can see from this point, all the buildings that my vision can touch. Get me the average era it was built, or only visualize the buildings I can see from here, and tell me, what their average, what their zoning codes are, and color coded in this way. Or you can draw a line or a circle or a closed curve and say, give me only the buildings within that closed curve. The sky's kind of the limit in terms of what kind of operation you can do with GIS in space. And that's, I think, the pretty exciting aspect of using Grasshopper and Rhino to do GIS, is that a lot of spatial calculations or spatial representations that you would be a lot more cumbersome to do is very easy in Rhino. You do have the trade-off that Rhino and Grasshopper, this GIS data becomes a little slow. I believe if you save this file, it's somewhere between 500 to a gigabyte, 500 megs to a gigabyte, but in exchange for that heaviness, you do get an unparalleled amount of freedom in terms of what you can do computationally to manipulate data in space.